So good morning, everyone. So we continue with circular motion, and I hope our mind also is not going circular motion. Mind is proceeding in the straight fashion, rectilinear motion. Yesterday we have come across a question, and we are going to do some more questions based on pseudo force due to rotating frame of reference. And I think some of you are not clear. What way? See, in previous case, when we did laws of motion, in case of rectilinear motion, we said when observer is having a linear acceleration in a particular direction, if the observer himself is accelerating, whenever he observes any object, so when he tries to apply his laws of motion on the object as seen from this frame of reference, we need to apply, if this mass is m, we need to apply a pseudo force. What is pseudo force? Because motion of the object in this frame appears to be different as seen for the ground frame. So yes, motion is different, acceleration is different. So there's some force also is different. And that force is called pseudo force. That force depends on, this is a linear acceleration. The pseudo force also is applied to object in the direction opposite to the acceleration of frame of reference. And it is mass times. So it depends on the mass of the object to which it is applied. And that is the expression we write. This is pseudo force. Now let's come what happens in case of this is when it has linear acceleration. Let's visualize a case. You just imagine this is kind of turntable and large turntable, and it is rotating with angular velocity omega. Now, so when this object is rotating, so this object is placed here, and this object also is not slipping. This object, a box is kept on the platform, and this whatever, it could be box or the block. This box also is undergoing circular motion, and distance from center of rotation is L. So when this object is undergoing circular motion, so if you look at real forces acting, so on the plane of this circular disk, there has to be force acting towards the center. Then only it will be turning in that direction. Otherwise, we're gone straight. And that force has to be equal to m mass into L into omega square. That's a force, a real force must be acting. And what is the real force acting on the object? If this is kept on a rough surface, the real force comes from frictional force. And if you look from the side, if you look from the top, mg is acting on this object, and normal reaction is acting, and the friction factor is acting in this direction. So friction force direction keeps changing, and that acts. So these are the real forces as seen from the ground. So if we observe from the ground, I will see this point going into circular motion of radius L, and this will be the real force it will act. Now imagine a different frame of reference. Just imagine you are standing on the platform and you are facing this block. So you have plates over, you are looking at the block. So if you take this as x-axis, you hold an arrow here. So you will see like this coordinate system. You hold a horizontal arrow and vertical arrow, and horizontal arrow is directed towards this object. You call that as an x-axis. And if you stand on the platform and you also rotate with the same velocity omega, in that case, what will happen? As this object has rotated, has come here, you are also rotated. Your x-axis also is rotated. So your frame of reference also is rotating. So in this case, this frame of reference also, if it is having angular velocity omega, in this frame of reference, this object will appear to be at rest. So that's the first thing what you need to understand. So what is the frame of reference? You understood here. So this axis also is rotated. So if you stand here, you hold a coordinate system. The coordinate system or the frame of reference is rotating with angular velocity omega. In that frame of reference, it will appear to be in equilibrium. But when we start applying here, the real forces are acting. What are the forces acting in this direction? There's a real force acting. This is not in equilibrium. So this also needs a correction. This also is in non-inertial frame of reference. When the observer rotates, so what is the correction? This is a real force, and net force has to become zero. So we need to apply, to make the net force zero, we need to apply a pseudo force. Which direction? To make the net force equal to zero. And the pseudo force what need to be applied is to make it zero is equal to same. So what is the pseudo force here? If I call Fs is equal to ml omega square. That's a pseudo force applied. So now in this frame of reference, if I apply pseudo force, again I apply laws of motion. I observe position of this object in this frame of reference is not changing. It is in this frame of reference, it is in the state of rest or equilibrium. Hence net force must be zero. This real force plus pseudo force both make it zero. In case of this, if I had another object here, another object which is m dash, which has a distance of some r here, on this I need to apply a different force because here the distance is different. So this pseudo force depends on combination of three things. What are three things? The pseudo force, mass of the object on which you're applying pseudo force, is distance from frame of reference from where the observer is, and angular velocity of observer. At what angular velocity is the frame rotating? And then when we apply pseudo force in that frame of reference, I can apply Newton's law of motion. That's how pseudo force. So this one is different from linear. So whenever we use pseudo force, or whenever you use a rotating frame of reference or linear frame of reference which is accelerating, you need to understand the difference between the two, and we need to apply accordingly. So pseudo force will come across a couple of questions which again involve something like this. So this is pseudo force when you apply, and so you notice here, ground frame, this motion is having circular motion. In this frame of reference, this object is at rest. They have different motion because the frame of reference is different, the way you're observing is different, and hence if accelerations are different, motion is different, the forces also need to be different. What is the difference? What is the corrective force we apply here? That's the pseudo force we apply. Now coming to one more small concept here, but basically understanding of concept of angular velocity. What is angular velocity? See, basically when we talk about angular velocity, it is linked to angular position of an object. And if the angular position changes, then it will have angular displacement and angular velocity. Let's try and understand. There's an observer here. So angular velocity is always with respect to observer. So where is an observer here? The observer is here. And let's see, there's one object which is undergoing circular motion. Let this radius be r, and it is having circular motion with angular velocity omega. So this particle v is equal to r omega, which is having circular motion. We know that one. If velocity is r omega, if its distance is r from here, angular velocity will be omega. Same instance, just imagine this one particle which is undergoing circular motion. There's a particle right next to it. This particle is not undergoing circular motion. This is moving in a straight path. Okay, so one particle, but at this instance, both of them have same linear velocity. Instantaneous velocity may be same. Little later, this is having circular motion, its velocity may change. But at this instance, so if as far as this observer is concerned, this object has angular velocity because its angular position is changing with time. Even this object also, what will happen as it moves, its angular position changes. So even this object also will have angular velocity. What angular velocity will have? Same as this other object. So what is angular velocity here? It is not necessarily the particle undergoes circular motion. Whenever its angular position changes, it will have angular velocity. And what will be the angular velocity here? So how do we understand angular velocity? So this is the case when it has tangential velocity. Let's imagine, suppose this object, rather than moving in the perpendicular direction, if the object had motion in the radial direction, if it moves towards O, will the angle made by the object at O with reference to some reference line? What is the reference line? Many times we take x-axis as the reference line. Its angular position is not changing, it means angular velocity is 0. So what we should understand here, angular velocity, whenever, first of all, we need to define an observer and an object. So whenever object has velocity, we can break it into two parts. Perpendicular means perpendicular to the radial vector, and the radial component. Radial component does not lead to angular velocity, whereas perpendicular component leads to angular velocity. So what I can write as angular velocity of any object is a perpendicular component of velocity divided by its distance, I can write, or we can write as perpendicular velocity divided by r. Whatever way we can write. If the distance is L, we can write as V perpendicular by L. So this is what concept of angular velocity is. And some question, it may become useful. If object is moving in radial direction, angular position will not change, and angular velocity is 0. Now come to this case. So in this case, if an object is like this is an object here, and this is an observer here. And object is and we always talk about instantaneous angular velocity. All cases we are talking about a very brief instance of time. So if at a particular instance, object is at a distance L from the observer, it can be any direction, doesn't matter. And it has a velocity V, which is an angle theta. angle theta with the line joining the object and the observer. So with reference to this observer, its angular, as it moves, its angular position is changing. What is the angular velocity of this object has? Again, what we'll do here, we'll resolve into two components. We'll take the perpendicular component and we take the radial component. Okay, which component is leading to angular velocity? Perpendicular component will be equal to v sine theta divided by the distance from the observer. This becomes the angular velocity, right? So this is the angular velocity in this particular case. So this was the case when observer was at rest. Sometimes we also need to calculate angular velocity in case of observer also in motion. So this is something I think is something like this. And you can imagine this one. And I'll give you one more idea about how to intuitively think about angular velocity. When two cars are moving in perpendicular road, so we are looking from the top. So we can call it is a vertical, is a kind of a helicopter view, you can say so. So if you're looking for a very high building, or if you're looking for a helicopter which is at rest, and so this is the motion. This is road junction here. And from road junction, one car A is approaching. It is at a distance of 60 meters. At this instance, the speed is 10 meters per second. Car B is from the junction, is a distance of 80 meters. And at this instance, the speed is 20 meters per second, right? So if you are sitting in car B, okay, so what is the angular velocity of car B as seen from A? So if you are at A, suppose you have a kind of a telescope or you have an arrow. If you have a telescope, if you are through telescope, you aim the telescope at B. So you know, so basically you're directly looking at B, but unless it is at particular angle, as these two cars are moving, you have to rotate the telescope at some angular speed, then only you can continuously watch car B. Why do we need to rotate this telescope here? Because angular position of B with respect to car A is changing. So you are holding a telescope. I hope you are able to understand this point here. So if you have a telescope and through telescope and you look at the car B only when telescope is aligned in that direction. So if at this particular instance, what is the angle it will make? At this instance, it will making an angle of 53 degrees. But this angle, as the cars move, you have to rotate, and the rate at which you rotate, the angular velocity which you rotate, thus the angular velocity of car B as seen from car A. That's what you may call as perhaps a practical example of angular velocity. And some questions also may be framed accordingly. So let's calculate when both objects are in motion. Angular velocity is V perpendicular by R, we know. When both are in motion, we attach frame of reference to observer. So we attach frame of reference here when we attach the coordinate system here, because this velocity is observed from the ground frame of reference. So if observer is placed here, then we'll have to car B also will acquire a relative velocity. If I place an observer, what does relative velocity do? So two ways of solving the question. One way of solving the question, moment we make A as an observer. If I make A as an observer, velocity of B will become VB minus VA. So basically we have done it earlier also. Relative velocity, I'll have to add a negative value of velocity of A. And that's what relative velocity. What is VBA equal to? Is equal to VB minus VA. So I'm adding negative velocity. What is negative velocity I added? At 10 meters per second. So this is 20 meters per second. This is 10 meters per second. So there are two velocities which are added. Now this velocity here, what is the angular velocity? It will depend on the distance. The distance becomes L here. And I have to take the perpendicular component. Since I have two things are there, I have to take the perpendicular component of this also, and I have to take perpendicular component of this also. And are these angles known? Yes, these angles are known. This angle is equal to 37 degree, and this angle is 53 degree. So one way I can calculate here, what is the perpendicular component here? So if I take perpendicular component here, one will be 20 sine 37. And other is under the opposite direction. So I'll put it as minus sign, minus 10 into sine 53. That is equal to perpendicular component of relative velocity. I divide by the distance here, distance is 100 meters. I get the angular velocity. Other way also, if you want to look at, we can visualize as perpendicular component of these two. So we have to take perpendicular component. I hope this is understood. We have taken relative velocity. And okay, so you want to visualize that also, something like this. So What we can do other way of is, this is what the motion is. Right now it is inclined. We can slightly rotate the whole thing. If I rotate the whole thing, it is something like this. I have made this line horizontal so that we better understand what is happening here. So it is the case here. This is A here. This is B here. If I taken this as x-axis and this as y-axis here, this is what the figure would look like. X-axis, y-axis, and what is this angle here? This angle is 53 degree, and this angle is 37 degree. So here also I could have calculated velocity of B with reference to A. And when I calculate this velocity, relative velocity, perpendicular component will be the y component. So whatever y component I arrive at, I divide by 100, I get the relative velocity. So I divide by say perpendicular component by distance, I get the angular velocity, and which comes equal to, so when we take this number, it comes equal to the, so we can easily calculate the difference of the two comes equal to 4 meters per second divided by 100. So angular velocity at this instance is 4 divided by 100 radian per second. So which way it has to be rotating, it will be rotating in this direction, and it will keep changing. It's an instantaneous angular velocity. Okay, so let's continue. So basically 2 parts we have done. One is pseudo force. We'll come across some more question which require understanding of pseudo force, and we can see some of the question can be solved in ground frame as well as in case of rotating frame of reference. Let's take example and let's try and understand the questions well, because the idea is not only to solve the question. The questions are a way to help a particular type of concept. A hollow cylindrical drum of radius r is rotating about a vertical axis with angular velocity omega. A small m is rotating. So there's small mass m here. Just assume, so it is like a drum. And can you think of any real life example of a rotating drum? Where can you think of a cylindrical drum, hollow cylindrical drum rotating about vertical axis? Has anyone seen this kind of thing? Yeah, if you look at you have top loading washing machine, you have front loading washing machine. This is an example of top loading washing machine. So if you look at the washing machine, there's a drum here. The drum also, once equal velocity, it is rotating constant steady state, constant angular velocity. And some of you, if you notice, when you put the time, when it stops, you can see the clothes here. Some of the clothes will be sticking to the vertical side of the wall. Because if something is up, and if you observe, you'll notice something similar. So let's assume here, there's a mass m here. So what we do, so there's a kind of cylindrical shell, which is set into rotation constant velocity omega. So there's a mass m here. Initially, let's say it's a transparent cylinder. Initially, there was some support which was holding this mass here. Otherwise, the mass would have slipped downwards. So initially, it was there. But once you start rotating with angular velocity omega, we remove this support also, still the mass does not fall. If something like this happens, let's try to understand why that would happen. So mass which is placed at a certain height against a vertical surface, typically we expect mass to start falling. It does not fall. If that is happening, so why is that happening and how would we explain this kind of observation? So what is the mass if I see? If I observe from the ground frame of reference, I will see this mass going into a circular motion of radius equal to radius of the shell. So it is undergoing circular motion. So if any object goes into horizontal circular motion, there must be net force acting in the horizontal direction towards center. So at this instance, so which is the direction, which is the direct net force acting? Net force acting on the object will be like this. That's the resultant force. Because it is no vertical direction, net force has to be 0. So which is net force here? And net force has to be equal to mr into omega square. Who's applying the net force? Only the contact force only can apply this force. So this would be the normal reaction here. Since the surface is vertical, the horizontal force applied by this vertical surface is called normal reaction. So the surface is applying a force equal to this. So, but this is making it go into circular motion. What is making forces in vertical direction to be 0? If I get vertical direction to be 0, let us see which are the forces acting here. One force, of course, we always know this mg is acting, but it is not sliding down. There's some force must be acting up. Where is the other force acting? This is a contact surface. So along the surface, friction force is also acting. And this friction force is maximum value can be equal to mu n. It can be anything less than or equal to this value. So if the object is not slipping downwards, it means the mg value is equal to friction force, or mg is less than mu n. Thus a condition for object not slipping downwards, or mg is less than mu times normal reaction, which is mr omega square. So that much friction must be present. So but moment we talk about minimum coefficient of friction, it always implies limiting state. Limiting state means friction is already reached its maximum. So let's look at this. I hope we have understood what is happening from the ground frame of reference. So what are the forces acting? This is a force acting in normal reaction, mg, because this is only contact force, other than contact force and gravitational force. And this is a condition here. Normal reaction is mr omega square directed towards center. State of limiting friction, friction is equal to mu n. So mu n is equal to this number. Friction force is equal to this number. And for no slipping, friction force has to be equal to mg. This will give you value of mu. Now that's how we can find it out. Okay. So this is what we have seen from the ground frame of reference. And God forbid, suppose you imagine yourself inside the cylindrical drum. So where are you? You are also inside the washing machine. And an observer, if you view from the top, this is the top, I think I have not drawn the top view. Let's look at the front. From the top, if we look like this, at a particular instant, this is rotating. And this is where the object is. If you observe from rotating frame of reference, so as the object moves here, your frame of reference also has rotated by same angular velocity omega. In this frame of reference, it will appear to be in a state of equilibrium. If it's in a state of equilibrium, I need to apply pseudo force. Pseudo force will be equal to mr omega square, and there will be a normal reaction also, as seen from the top. And as we see from the top, we are seeing the horizontal forces. So here also, since it is in equilibrium, this also leads to normal reaction equal to mr omega square. And the pseudo force what you applied is called centrifugal force. So centrifugal force exists only when you make observation from rotating frame of reference. Otherwise, there's nothing called centrifugal force. It's a pseudo force. This one, if it's set into rotation, what would be if angular velocity is omega? So basically, let's assume it's the whole thing is rotating. Initially, through some means, I hold this object in a state of rest. Suddenly, we release it. So angular velocity omega is constant. Whole thing is kept in a horizontal plane. This is smooth surface here. What would be the tension in the string? That's one part. And then we can also calculate what would be the acceleration of two masses here. What basis do we calculate? What basis we solve this question? So again, to solve such question, and in this case, what are we assuming here? So release from rest. And this question, we assume that the direction, see, in this case also, the string is in a direction parallel to the radial direction. Even if it is not mentioned, we need to assume that it remains in the direction parallel to the radial direction. So how do we solve? So we could have solved in ground frame of reference. We can also solve in rotating frame of reference. Let's this time, previous question also I could have done from rotating frame of reference. In that case, previous question, friction force would have become equal to centrifugal force. So let's do from a frame of reference which itself is in rotation. So where are you? Your port self, you are here. And you are looking directly at the pulley, and you hold an arrow and you call that an x direction. So and when as this pulley rotates, it comes here, your x also comes here, kind of thing. So you are also rotating the same angular velocity as the whole system is rotating about this point. So when I observe from here, so that's in that case, what will happen? From ground, I see these objects going into circular motion, and moment they start slipping, it will have complex motion. But if I see from frame of reference standing on the platform, which itself is rotating, it becomes like a radial motion. It becomes a little easy. So direction of acceleration becomes, so motion is easier to understand from rotating frame of reference. So first thing what we notice here, in ground frame, if I take ground frame, moment as soon after release, what kind of motion it will have? if I have to define what is motion soon after release, will these two objects have a circular motion? No, they will not have circular motion. They will have kind of spiral motion, which is difficult to analyze. But if I use a rotating frame of reference, rotating with omega, then motion is better understood. Motion is easier. What kind of acceleration it will have only? The acceleration of m and 2m. Both will be in the radial direction only, one away and one towards. That's important. That becomes easy. So which frame I use? So we'll solve this question in rotating frame of reference. What is my frame of reference now? Omega. So moment now, if I draw free body diagram, since I have to calculate tension, force and all. So first, I need to draw, again, the way we draw, mark all the forces and draw the free body diagram. So let's do that one. If I draw the free body diagram, what is the condition in this frame of reference also? If this block has a radial acceleration of A away, this block will have acceleration A towards. That's a condition for, that's a constraint condition from this frame of reference. So whatever velocity it will appear to be going away, whatever acceleration, this object will appear to be moving towards the same acceleration. Or in this frame of reference, if this moves by 1 meter, this has to move closer by 1 meter. So this is a condition. Let me mark the forces now. And we are concerned only with horizontal component of forces, which are easy to mark now. So let's mark what are the forces which are acting. Pretty simple. On this force here acting will be equal to T, tension here. And what is the force acting? Centrifugal force, since I am using circular frame of rotating frame of reference. Mass of the object to which I am applying pseudo force, mass, into its distance from observer, rotating observer, R, into omega square. That's the centrifugal force. And I come to this part also. So in this object also, if I draw free body diagram, this also will be T. And centrifugal force will be mass is 2m into its distance from axis of rotation R into omega square. Now I write the condition for motion. So this I mark the free body diagram. Now a simple way, the way we solve in case of linear motion, it becomes similar here. So for small m, let me mark the forces. A will be equal to acceleration will be equal to forces in that direction, T minus mr omega square by m. That's the acceleration of that block. So force acting in this direction of acceleration is positive. For this block I have taken this is positive. For this block we take this as positive. Now for 2m, if I write the explanation, this will be A is equal to, what will the equation here? Now this direction is positive. So 2mr omega square minus T by 2m. If we equate those two, we get the value of T. So this is the question, I think, when it is rotating, and this question is best solved in rotating frame of reference. If you do in ground frame, it becomes a little complicated because then in that case it's difficult to little bit understand. Right, view from rotating frame of reference. Okay, so one more question before I move on to vertical circular motion is about power. See, even when object moves in a circular motion, if it is uniform circular motion, we know the kinetic energy does not change. But if it is not uniform acceleration, we have seen some cases, one of the example like rod also rotating the ring. So if it has tangential acceleration, its kinetic energy will change. If kinetic energy is changing, it means power energy is being supplied, work is being done, and rate of work and power also is involved. So let's suppose there's some question on that. What is given in moving circle is a constant radius. So moment is a constant radius. Yes, we can apply circular motion property. Radial acceleration is changing as this. This is what is given. Radial acceleration is changing. If radial acceleration is changing, what is radial acceleration equal to? Radial acceleration is equal to v squared by r. So if radial acceleration is changing, r being constant, very clearly it tells me that velocity is changing. If velocity is changing, it means kinetic energy is changing. If kinetic energy is changing, it means some work is being done, energy is being supplied, and rate at which energy is supplied is power. So we understand here there's some power being supplied here. Let's see how do we solve it. So this information given, we need to calculate what is the power required for this kind of motion as function of time. So this is given, and let's understand first of all what are this term here. Let's write in a form which is easier to understand. AR is given as is equal to V square by R, which is equal to K2. This is the first information given. Now let's look at what we need to find and see how do we use what we need to do. What is power in case of circular motion? See, power term is equal to what? Moment we talk power, power is equal to dot product of force and velocity. But when we talk about circular motion, so when we talk about circular motion, force also we can take into two parts. So any part, it is velocity v. But what is the direction of force when it is having circular motion? See, it is accelerated circular motion. So it may have, so forces also we always talk about two components. Tangential component it may have centripetal component. So when we talk about dot product, actually it is dot product is equivalent to Ft into V. That's what it is. And what is Ft equal to? Tangential force. Tangential force is equal to m into at into V. Or at is equal to dv by dt into V. That's the power. So I hope this part is clear. If that is what is power, so this is what I need to find. I need to find product of velocity and its derivative with time. Okay, when it's changing with time, then only power is energy is changing and power is being supplied. Or other way, how could I calculate power? That's one way to calculate power. Other way I could have calculated power. Whatever power is going, it is going into rate of change of kinetic energy. That also is power. So I could have also done d by dt of 1 by 2 mv square. If I do so, 1 by 2m into 2v into dv by dt, and we find both expressions are same. And it has to come out to same. So either way, I understand this is what is given, and this is what I need to find. From here, how do I get this expression? Very clearly, I need to differentiate this term with reference to time. So once we do that, we write that term, is very easy. Power is equal to this. We need to differentiate with reference to time. And when I differentiate both sides with reference to time, I get 2v by r dv by dt is equal to nkt minus 1. That's the value. And once we have v into dv by dt, I substitute this value here. I get the value of power. So that's the whole analysis. I hope all this is understood. All are clear so far?